Is a world like Pandora possible? This question was buzzing in my head as I left a recent screening of the movie Avatar: The Way of Water. I'm sure a lot of you have seen Avatar or its sequel, or at the very least have heard about them. But in case you've been living under a rock, or there weren't any cinemas on the desert island where you were shipwrecked, here's the short version. Both Avatar movies are set on Pandora, an Earth-like moon in the Alpha Centauri A system. After Earth exhausts nearly all of its natural resources, humans set their sights on colonizing Pandora, which hosts highly developed ecosystems of interconnected life forms, among them a species of technologically primitive but physically evolved humanoids called the Na'vi. There is, of course, a lot more to it: interstellar travel, genetic engineering, and memory implants, all of which are really interesting. But this video is concerned with the science of Pandora itself. How much is based on real science? What did director James Cameron and his team get right? What did they get wrong? And although it might sound far-fetched, could there theoretically be a world like Pandora out there? I'm Alex McColgan, and you're watching Astrum. Join with me today for a fun thought experiment as we turn our telescopes to the fictional world of Pandora and analyze the moon's complex geology, orbital mechanics, biosphere, and atmosphere. Let's start by looking at the Alpha Centauri A system where Avatar is set. Alpha Centauri is a 3-star system in the Milky Way galaxy, comprised of 2 sun-like stars, Alpha Centauri A and B, and a small red dwarf, Alpha Centauri C, also known as Proxima Centauri. As the closest neighbouring star system to our own, it's a convenient place to visit. Of course, in interstellar terms, convenience is relative. Alpha Centauri is 4.37 light-years away from Earth, meaning it would take a spaceship travelling at the speed of Voyager 1 over 70,000 years to get there. But let's assume humanity develops technology capable of interstellar spaceflight, as it has in the Avatar movies, even though the original start date of 2154 still might be a bit optimistic. Alpha Centauri A actually has a few things going for it as far as habitability is concerned. Its star is only a bit bigger and brighter than our Sun, meaning it has a Goldilocks zone, not too hot, not too cold, around 1.2 astronomical units from its center, where liquid water could exist on rocky worlds orbiting it there. A good start for the science of the film. But despite Pandora's Earth-like appearance, one notable difference is that it isn't a planet. It's a moon orbiting the hypothetical gas giant Polyphemus. Here too, the films are on a pretty sound scientific footing. There are most likely many more moons than planets in the Milky Way galaxy, meaning the chances of finding a moon with the right conditions for life are that much greater. And even within our own solar system, we know of several moons that could be hospitable to life. 2 of those, Europa and Ganymede, orbit Jupiter, a gas giant like Polyphemus. Enceladus, which orbits Saturn, is another. But on all these moons, any potential life would exist in oceans that we think lie underneath their frozen surfaces. Pandora, on the other hand, has Earth-like oceans on its surface, which are on full display in Avatar: The Way of Water. And any surface life would likely face significant challenges. Gas giants have intense radiation belts made of electrons and ions trapped by their strong magnetic fields. So any life on Pandora's surface had better be up to the task of dealing with some serious radiation. There might be offsetting factors though, such as a buffer from its atmosphere. Pandora could also have its own magnetic field for protection, and there's some strong evidence for this explanation. We see indirect evidence in the form of Aurora and the film's floating Hallelujah Mountains, both of which I'll discuss in a bit, so hold that thought. Avatar's fan wiki proposes the alternative explanation that Pandora resides outside the main radiation belt, except for 1 week when it passes through Polyphemus' night side. Allegedly, this is when the aurora occurs on Pandora. Whether or not this was James Cameron's intention, it seems that Pandora's life has evolved to survive in a particularly harsh environment, and I, for one, wouldn't question the toughness of the Na'vi. In real life, we have yet to confirm a gas giant orbiting any of the Alpha Centauri stars, although there is some debate as to whether a possible giant called Candidate 1 might be orbiting Alpha Centauri A. Candidate 1 was first spotted using mid-infrared technology in 2021, which is over a decade after the first Avatar movie came out. Incredibly, scientists believe it would orbit right in Alpha Centauri A's habitable zone. But before you get too excited about the discovery of a real-life Polyphemus, be aware that scientists still aren't sure if it's really an exoplanet or just an artifact caused by a cloud of dust. If it is a planet, it would likely have at least the mass of Neptune, or in other words, a gas giant. We'll have to await further evidence to evaluate this one. But in 2016, scientists discovered something just as cool orbiting Proxima Centauri's habitable zone, a planet that is Earth-like in size. Seeing as Proxima Centauri is a really old and tiny star, there is, however, debate surrounding how habitable this world really is. Our ability to detect exoplanets has gotten way better in recent years and continues to improve, so it's likely we'll continue to find exoplanets that are potentially habitable. Regardless, whether or not Alpha Centauri A has a planet like Polyphemus isn't crucial to this exercise. Polyphemus could exist anywhere in the universe as far as we're concerned. One of the more unusual aspects of the Avatar movies is how they handle Pandora's day-night cycle. In both movies, there is a night-like phenomenon referred to as eclipse by the Na'vi. This is showcased spectacularly, as Pandora's inhabitants experience an ethereal twilight when the moon enters the shadow of its parent planet, Polyphemus. This is a rather beautiful bit of world building, as Pandora would likely experience a regular darkening event, like our rarer total solar eclipses on Earth, which would coincide with the eclipse of Alpha Centauri A behind its parent planet. These eclipses would probably be experienced as a relatively short darkening, while a second, longer night phenomenon would occur due to the moon's rotation. I also love how night on Pandora takes on a twilight appearance. This makes sense, given the relative proximity of Alpha Centauri B, which would still be an extremely bright star when Alpha Centauri A is occluded. When you factor in the bioluminescence of Pandora's many flora and fauna, what you get is a shimmering, twilight world with enough scientific grounding to pass muster. As for how long night lasts on Pandora, James Cameron has yet to spill the beans, but there's some interesting speculation among the film's devoted fanbase. Avatar's fandom wiki conjectures that Pandoran eclipses are 100 minutes long and nights are 34 to 35 hours. Since Pandora is probably tidally locked to Polyphemus, it might take just 60 to 70 hours to complete its orbit. Remember, when a moon is tidally locked to its parent, like ours is, its orbital period and rotation are the same duration, which is why we always see the same side of the moon from our standpoint on Earth. Io orbits Jupiter in 1.8 Earth days, for instance, so a 60-hour Pandoran orbit isn't out of the question. This leads to a fascinating inference. If you are on the side of the moon that sees Polyphemus, it will always be in the same place in the sky, whereas on the far side of Pandora, you wouldn't see the planet at all, or any eclipses. So any natives living on the far side might not even know they're orbiting a planet. If any of you have your own theories about Pandora's day-night cycle, please let me know in the comments. Your guesses might be better than the ones I was able to find. Next, let's talk about Pandora's atmosphere. According to the films, it's a mix of nitrogen, oxygen, carbon dioxide, xenon, methane, ammonia, and hydrogen sulfide. Unfortunately for humans, the latter three are unbreathable, and the high quantities of carbon dioxide, allegedly 16 to 18%, are also a no-go for humankind. But humans developed under the unique atmospheric conditions of Earth. Theoretically, life under Pandora's alien conditions would evolve differently. I appreciate that the movies put a lot of thought into this. It's addressed with the anatomy of the Na'vi, who have special organs called wichao, which combine carbon dioxide with water and convert them into oxygen and methane. Despite Pandora's high CO2 levels, it also has higher levels of oxygen than Earth's atmosphere. Combine this with the oxygen-generating Wichao and the Moon's 20% reduced gravity compared to Earth, and you can see why the fauna on Pandora grows so big and strong. More oxygen in the atmosphere in the ancient past is why dinosaurs got to grow so tall on Earth after all. Another interesting fact is that Pandora's heavier mix of gases and denser atmosphere at sea level means acceleration requires more force. Humans would experience this like a wind blowing against them as they walk, whereas the Na'vi are equipped to overcome this resistance with thin, muscular frames and tensile toes for gripping the ground. Pandora's unique atmosphere manifests in other ways too. My absolute favorite touch is the aurora that appear in the way of water, which appears bluish and violet. On Earth, most aurora are green, which is the product of solar winds exciting oxygen and nitrogen molecules under a given set of barometric conditions, although we do rarely get red, violet, or even yellow auroras. It's no surprise that these phenomena might look different on Pandora. On Jupiter and several of its moons, for example, aurora are blue, while on Saturn they are largely in the ultraviolet and infrared bands of the spectrum. On Pandora, these different colors could be the result of differences in atmospheric composition, pressure, and the strength of its magnetic field. So far, I'm actually surprised by how much Pandora is pretty plausible. But I know there's a question you're waiting to ask, so let's get down to it. How realistic are the film's iconic floating Hallelujah Mountains? Well, there's good news and bad news. The good news is physicists at Yale and Penn State say floating masses produced by magnetic repulsion could, theoretically, be possible. Unfortunately, you would expect this phenomenon to require extremely low levels of gravity, incompatible with the locale's iconic waterfalls and with how gravity is generally represented on Pandora. But there could be another explanation. After all, the mountains are rich with Pandora's iconic precious metal unobtainium, which is described as a powerful superconductor. In fact, the prospect of mining unobtainium is what brings humans to Pandora in the first place. In theory, if there were a magnetic bubble on the moon's surface, this could produce an effect in the unobtainium-rich mountains similar to how maglev trains float above their tracks. Given that unobtainium is a theoretical metal, I'll give this one an incomplete. Are floating mountains likely? Not exactly, but we should at least leave the door open to such a phenomenon being possible. Having said that, the Hallelujah Mountains are based closely in appearance to the mountains of China's Changchacha National Forest Park, minus the floating part. So if you want to see the closest thing to Avatar's most spectacular feature, you might want to book your next ticket to Changchacha. So there we have it, a walkthrough of some of Pandora's likely, not so likely, and seemingly impossible attributes. Overall, I'm really impressed with how well Avatar held up to this thought experiment. James Cameron has said on several occasions that Avatar is meant to be a space fantasy, but for a fantasy, it's one that clearly has a lot of thought and research put into it. When you factor in the film's important message about ecological preservation, there's a lot for the scientific community to embrace and appreciate. And who knows, maybe future discoveries will make some of Avatar's more outlandish predictions look prescient. I'm looking at you, floating mountains. If you're anything like me, you've been impatiently waiting for Dune Part 2 since they announced it a couple of years ago. I saw it in the cinema the other day, and let me tell you, it did not disappoint. In case you aren't familiar with the Dune universe, here's a quick rundown. Dune is a book series written in the mid-1960s by Frank Herbert. It's regarded by many as one of the best works of science fiction of all time. The first book alone is almost 900 pages long, which has since been made into a 2-part movie. The Dune universe is incredibly rich in scientific concepts like interstellar travel, personal shields based on subatomic particles, human adaptation to incredibly harsh environments, moons that tilt the rotational axis of their planets, and so much more. It got me thinking, how realistic are these ideas? Are they really just science fiction? or somewhere within the realm of possibility. I'm Alex McColgan, and you're watching Astrum. Join me today as we dive into Dune to uncover how much this pioneering work of science fiction stacks up as science and how much as fiction. Dune revolves heavily around the use of interstellar, faster-than-light travel, which is necessary given the story spans several different worlds and galaxies. In fact, the author himself notes in an appendix that there are over 13,000 planets in the Dune universe. That's a lot of planets. So let's focus on the main three: Gedi Prime, Caladan, and Arrakis. Gedi Prime is home to the Harkonnen, the current stewards of Arrakis and its resources, which we'll get to later in the video. It's a highly industrialized world where little photosynthesis occurs, meaning they would probably be dependent on trade with other worlds for their food needs. They've replaced almost all natural things with built environments, except for a slither of forest maintained for logging. Caladan, by contrast, is a lush, oceanic world, home of the Atreides and our main character, Paul. Water is abundant and the weather is pretty mild. Both these worlds couldn't be more different from Arrakis, where most of the action happens in the movie. Let's take a closer look. Arrakis is a desert world that makes the Sahara look like an oasis. It is the third planet from its sun, Canopus, orbiting at a mean distance of 87 million kilometers. That's about twice as close as the Earth is from our sun. If we were that close, it would be pretty hard for life to exist, given the searing hot temperatures and ultra-high radiation. So, can Arrakis support human life? It's possible Herbert drew inspiration from an actual star called Canopus, a white star in the southern constellation of Carina. At the moment, this star is in its blue loop phase of stellar evolution, where it changes from a cool star to a hotter one before cooling again. Meaning, at times Canopus could have been considerably cooler and dimmer than many yellow dwarf stars like our sun. This would have positioned Arrakis in the sweet spot of its star's Goldilocks zone at some point in its stellar cycle, making conditions more suitable for supporting life. Something I think is super interesting about Arrakis is its orbit. Just like Earth, Arrakis sits third in line from its star, but that's where the similarities end. On either side of Arrakis are two much larger planets known as the Twins. Thanks to the dedicated fans over the Dune fandom wiki pages, who have accumulated an extensive amount of information about the Dune universe, we know the Twins have elliptical orbits. These orbits pull Arrakis into a gravitational tug-of-war, which causes shifting and changing Arrakis' orbital pattern. A year on Arrakis can range from 295 to 595 standard days. I wonder if we'd ever seen an example of something similar in our own universe. Turns out highly elliptical orbits are not so uncommon. We've discovered quite a few exoplanets that follow this pattern. We also know that highly eccentric orbits can influence the orbit of other nearby planetary bodies within the same system, such as a change in orbital inclination, shifts in the orbital period, or even orbital resonance. However, I think the kind of drastic variation we see on Arrakis is highly unlikely in our universe, because it would require very specific, unstable, and chaotic conditions to exist. Even then, the scenario would be short-lived. Speaking of orbits, Arrakis also has a couple of moons worth mentioning. Kreln and Arvon are both visible in the Arrakis night sky. Kreln, the larger of the two, shares a lot of characteristics with our own moon. It orbits every 25.5 days, is covered in a thin layer of meteoric dust, is speckled by craters, and has no atmosphere. Arvon is much smaller and completes an orbit every 5.7 days. While the Twins affect the length of the year on Arrakis, these moons affect the length of the day by influencing how fast Arrakis rotates about its own axis. The average day is about 22.5 standard hours long. However, under special circumstances, the day can be as short as 3.8 hours and as long as 51.4 hours. Based on what we know about astrophysics, this kind of scenario seems highly improbable. Planetary rotation is mainly determined by the conservation of angular momentum, it's pretty hard to change this momentum without an external force being applied. Technically, the moon's gravities would be an external force, but it's also improbable that alone would be enough to cause such strong fluctuations in Arrakis' rotation. Similar to the dynamic between Arrakis and the twins, this configuration would also likely be highly unstable and short-lived in practice. Let's move on to two of the biggest sci-fi tropes these films deal with: force fields and interstellar travel. In the Dune universe, both of these technologies hinge on the same fictional principle, known as the Holtzman effect. I won't go into too much detail about it, but it basically has to do with the supposed repellent properties of subatomic particles. Let's start with the force fields, which take shape as personal shields in the film. We see lots of different characters using these shields during combat. They're generated around the wearer by the Holtzman effect, creating a defensive barrier that is impenetrable to fast-moving objects like bullets. Slower-moving objects like a blade, for example, can still penetrate the shield. Scientists have made numerous, mostly unsuccessful, attempts at creating force fields or invisible shields in real life. Most have so far focused on electromagnetism and plasma. We haven't looked at subatomic methods yet, so for now this will have to remain in the realm of fiction. I'm also not sure of the scientific reason why a subatomic force field would protect its user from fast objects, but not slow ones. Perhaps it was simply to move the plot along, or to introduce more tantalizing fight scenes. If the Dune force fields worked against everything, there would be no place for epic hand-to-hand combat, and wouldn't that be a shame? This aside, the shields themselves are obviously way beyond our current technological capabilities. We are only just starting to understand how subatomic particles like bosons and quarks work, and so far they seem to be incredibly difficult to predict. Even if we could predict them, it's unclear how they'd interact with matter to produce the protective barrier we see in the films. And then there's the issue of conservation of energy. The energy from the fast-moving objects that are repelled by the shield must go somewhere. You'd expect some kind of change to the shield, whether kinetic or thermal. The shields in the movies light up when hit, but it is unclear how the Holtzman effect turns kinetic energy into heat and then light. The other major application of the never-explained Holtzman effect is space folding, a key component of interstellar travel along with the spice, which we'll get to in a second. With the help of a Holtzman generator, space navigators known as the Guild Navigators can literally fold space, allowing spacecraft to travel faster than the speed of light. Right off the bat, we know nothing can surpass the speed of light without violating the known laws of physics. There are a few main reasons for this, and they boil down to Einstein's theory of relativity. Firstly, as a starship accelerates, time will begin to dilate relative to a stationary observer. As they approach the speed of light, time would effectively stand still for the crew. Traveling faster than light then implies some kind of negative time. And it's in going down this rabbit hole that we end up with things like the grandfather paradox and other time loop paradoxes we've discussed before on this channel. Secondly, a starship approaching the speed of light will also approach infinite mass, meaning you need infinite energy to accelerate past that speed. What the source of that energy would be is unclear. But from the way the director portrays it in the film, it seems the ship somehow fold space, perhaps with a wormhole, to arrive at their destination in no time at all. We've already discussed the science of wormholes in our analysis of Interstellar, which you can watch here. The second half of the interstellar travel equation is a mystical blue powder known as the spice. It has incredible economic and political importance in the Dune universe, because without it, interstellar travel would be impossible. The only way you could find this spice is Arrakis. It facilitates interstellar travel by eliciting its effects on the pilots, not the starships themselves. Let me explain. The spice imparts some pretty crazy effects to the person who consumes it. To the indigenous people of Arrakis, known as the Fremen, it is considered sacred. it has very strong anti-aging properties that helps you achieve a state of prescience by expanding your consciousness, enabling you to see the future. However, it is also crazy addictive, and withdrawal from it will kill you. The guild navigators take this spice when piloting a starship to help them achieve that state of heightened awareness. The precognitive effects allow them to successfully navigate folded space and safely guide starships across interstellar space instantaneously. Now, obviously we don't know of any substance that can help us see into the future, otherwise the entire gambling industry would collapse overnight, but that would be the least of my concerns. Seeing into the future implies knowledge of events before they occur, which violates the laws of causality. The effect must follow the cause, not the other way around. With precognition, you get paradoxes like time loops. It also violates the law of information conservation, which says no new information can be created or destroyed in a closed system. The closest thing to the spice that might come to mind are psychedelic substances, which humans all over the world have used to connect with heightened states of consciousness for millennia. These psychoactive plants are also held as sacred by the indigenous people who use them, just like the spice is seen as sacred by the Fremen of Arrakis. That being said, there's no way eating a magic mushroom on a spaceship will make it reach the speed of light. Another sacred substance on Arrakis is water. The planet is a total desert, without any natural precipitation or surface water bodies. The only water the Fremen have access to is stored in underground wells, which they don't dare to use, because they dream to one day use this water to terraform Arrakis, make it more hospitable, and reclaim their power from the oppressive empire. The only other water source they have are the byproducts of their own bodily processes. As you can imagine, this has led to some pretty hardcore water recycling practices. You definitely notice the full body suits the Fremen put on whenever they venture out of their underground communities. They are known as still suits, and are designed to capture and recycle as much bodily water as possible. They filter sweat, blood, urine, and other secretions through a series of microdermal layers. Once the water is separated, it goes to a collection pocket. The Fremen then drink this water through a tube, kind of like a camel pack. It sounds disgusting, but also intriguing. How would that work if we tried to build a still suit? First off, we'd need a material that can filter things at the microscopic level to separate waste from water. This actually exists. It's known as a nanoporous membrane, and it is made of nanopores so small they only allow water to filter through. Everything else that is too big, like bacteria, will be held back. On Earth, these membranes are made from a mix of materials that sadly would be hard to come by on Arrakis, namely metals, ceramics, and polymers. The second big hurdle I see to these suits is keeping them hygienic. Turns out there are a few different ways to clean and maintain nanoporous membranes, but only 2 of them seem plausible on Arrakis. The Fremen would either need to dry scrub their still suits with brushes, or apply air pressure through some kind of handheld pump. While it is theoretically plausible for us to use our existing technologies to make a very basic version of something like this, I doubt many people beyond maybe Bear Grylls and other extreme survival experts would be up for trying it out. With Arrakis being a desert planet, there's not much in the way of alien life forms to discuss. However, there is one very impressive creature that seems too big to be true: the sandworm. First off, how could a creature that big survive without much to eat in the desert? Well, you might be familiar with a similarly large creature on Earth that has found a solution to this problem. Apparently, sandworms feed kind of like blue whales. They guzzle huge amounts of desert sand and filter out the microscopic sand plankton living there. Okay, but does the maths add up? Blue whales can eat anywhere from 1 to 4 tons of plankton per day during the summer feeding season. They are about 25 meters in length and can only feed in Arctic waters, which make up 1.3% of the total ocean water. Not accounting for differences in metabolism, a 200-meter long sandworm feeding at the same rate would need about 8 to 35 tons of sand plankton per day. That's a huge number. But if you consider they have 100% of the planet's surface to feed, compared to the whale's 1.3%, I guess they could sustain themselves like that. They don't rely on water to live though, and I'm not aware of a single organism, even the most hardy extremophile, that doesn't rely on water in some capacity to survive. Speaking of water, let's talk about terraforming Arrakis. One big goal of the Fremen is to turn at least parts of Arrakis into a lush, green, and more hospitable world. That's why their underground wells are so precious to them. Any kind of terraforming would have to start with water. What I'm about to say isn't shown in either film, but it is a spoiler from the books, so if you are planning to or are already reading them, you might want to skip this part. Several thousand years in the future from when the movies are set, Arrakis is indeed successfully terraformed by the ruling powers. I couldn't find much about how this was done, but that didn't stop me from coming up with some ideas of my own. Terraforming a pure desert into a temperate climate is a super ambitious undertaking, limited mostly by time. It isn't a project you could do in a lifetime. Luckily for the people of Arrakis, the spice serves as a fountain of youth, so the time constraint is not such an issue. It makes me think of similar ideas we've had on Earth about terraforming Mars, including NASA's software system architect Casey Hanmer's idea to send a fleet of solar sails to Mars to sublimate the planet's frozen carbon dioxide and thicken the atmosphere. Another, slightly less delicate suggestion put forward by Elon Musk is to drop 10,000 nuclear bombs on the polar ice caps to release carbon dioxide and water vapor. Thickening the atmosphere would warm the planet to more Earth-like temperatures, but scientists still don't agree whether there is enough frozen carbon dioxide on Mars for this approach to work. The atmosphere on Arrakis is already Earth-like. To kickstart the terraforming process there, I'm assuming you'd need to import water from other planets. Other things to consider include soil quality, climate modification, ecosystem restoration, and overall climatic stability. You'd also have to introduce species to build and maintain varied and resilient ecosystems, which something the Emperor at the time of Arrakis' terraforming did actually do. In my opinion, Dune really stacks up to its reputation as a pioneer of the sci-fi genre. It's got everything you could want: multiple worlds, interstellar travel, force fields, weird alien creatures, and mystical powders with seemingly magical properties. Dune was never meant to be scientifically accurate. It really puts the fiction in science fiction and encourages us to use our imaginations. Fictional universes give us an opportunity to explore what we do and don't yet know, deepening our understanding of physics and get a sense of where the current limits of science lie. As Albert Einstein himself said, imagination is more important than knowledge. Knowledge is limited, whereas imagination embraces the entire world, stimulating progress and giving birth to evolution. And that makes sci-fis like Dune worth keeping around. What's the most terrifying creature that you can imagine? Walking out of the cinema after watching Alien Romulus, the latest film in the infamous Alien franchise, with adrenaline still coursing through my earthly human veins, I couldn't stop thinking that the answer, for me, was the monstrous beings I had just witnessed on the big screen inside. And I suspect I'm not the only one. Ever since the first Alien film was released in 1979, the creatures terrorizing the inhabitants of the many ships and planets in the series have captured the attention of audiences across the world, and over those 40 plus years, held it with a vice-like, almost face-hugger level grip. And now, with this most recent venture into the Alien universe springing up onto our screens, I want to find out, how scared should we be? Could these types of creatures and the worlds they spawn from even be possible or real? Will we ever venture far enough out into the universe to find other frightening examples of life? Or is the real threat much closer to home than we realize? From a scientific perspective, There is so much to unpack across the 9 films in the anthology. We have astronomy, astrobiology, chemistry, long-duration space travel, and astroarchaeology, all forming important aspects of these stories. So let's get into them and find out what holds water and what dissolves like metal under xenomorph blood. I'm Alex McColgan and you're watching Astrum. Join me today as we probe the Alien films to find out what's science and what's fiction.
Big things have small beginnings.
If you haven't seen the Alien films, or perhaps if you have but can't recall what happened with their continually sprawling plot lines, here's a quick recap. The first film, starring the brilliant Sigourney Weaver as the iconic heroine, Ellen Ripley, begins with the crew of the spaceship Nostromo responding to a distress call from a derelict ship on the moon of a gas giant. Upon entering the ship, one of the crew encounters an alien creature. And by encounters, I mean it jumps and latches onto his face, bringing him unwillingly into the complex life cycle of the xenomorph. The xenomorph, through the various stages of its biology, proceeds to wreak fear and destruction across the ship, and indeed across multiple films, with the rest of the franchise fleshing out the origins and subtleties of these fascinating life forms in different places and times. But where are these places, and when are these times? Following the entire multi-film timeline, some of the earliest events take place during the 5th film in the franchise, Prometheus, set in the year 2089, not too far in the future. The main character of Prometheus, Dr. Elizabeth Shaw, is performing an astroarchaeology survey, where she and her team are studying cave paintings on the Isle of Skye off the coast of Scotland. They are searching for clues of ancient astronomical phenomena in the artwork of prehistoric humans. This is actually a fascinating part of real-world astronomy. By working like some kind of space Indiana Jones, studying rock carvings and paintings, scientists have been able to uncover significant cosmic events like comet impacts and supernovae that once lit up our night skies. For example, the carvings at Göbekli Tepe in Turkey are believed to chronicle a massive comet strike around 11,000 BC, an event thought to have ushered in a period of significant climate change known as the Younger Dryas, a mini ice age which profoundly affected early human societies. In Prometheus, Shaw's team find depictions of a towering human-like figure pointing towards a star in a constellation, and a constellation the characters seem to have seen before. They interpret the image's message as this entity encouraging humanity to go to that star and explore it. This constellation, and the star, are real. If you're standing on the southern hemisphere at night, you can make out the faint constellation of Reticulum for yourself, with the star Zeta Reticuli nestled inside it. The constellation matches up pretty well with the drawing seen in the cave scene, although it's not an exact match, which makes sense because stars move over time, a process known as proper motion. So when these drawings were made some 35,000 years ago, the pattern would have looked slightly different. However, despite this precision, this southern constellation is definitely not something the ancient humans on the Isle of Skye would have been tracing out from their position up on the north of our planet, so -1 point for accuracy there. Zeta Reticuli is a binary system, meaning two stars gravitationally bound to one another. Set at a distance of 39 light-years from Earth, both stars are sun-like in their mass, size, and luminosity. They orbit each other at about 4,000 times the distance that Earth orbits the Sun. And in the films, the slightly larger of these stars, Zeta II Reticuli, is home to a ringed gas giant planet called Calpamus. Calpamus's moons are the setting for the first encounters of humanity with the xenomorphs, and even perhaps their creators. Habitable moons around gas giant planets are a familiar sight in science fiction films nowadays. In our Avatar video, we talked about the perils and pleasures of life thriving on the moon of a gas giant. However, LV-426 and LV-223, the two moons of interest around Calpamus, are nowhere near as lush and enticing as the oasis of Pandora. Both are barren rocks with few signs of life, and atmospheres that are toxic to humans. And the way the moons are represented may make them somewhat toxic to physics nerds too. LV-426, also known as Acheron, has been subject of inconsistency across the films. The moon was described as having a diameter of just 1,200 kilometers, about a third the size of our Earth's moon, which, despite its small size, was said to have a surface gravity of 0.86 g, implying a ridiculously dense composition that cannot be found on any other moons or asteroids. To put this into perspective, a moon with such gravity and size would have an average density of around 48 grams per centimeter cubed. This is about 10 times higher than our planet at about 5.51 grams per centimeter cubed, which is made up mostly of iron. LV-426 would have an average density more than twice that of uranium's 19.1 grams per centimeter cubed, and would be over 4 times denser than lead at 11.34 grams per centimeter cubed. In fact, it's only a third the density of the Sun's core, which is 150 grams per centimeter cubed. Additionally, at such a small size, the surface would be noticeably curved to anyone standing on it. Even flat Acheroners wouldn't be able to deny it. But unfortunately, this curvature is not visible in any of the scenes on the moon's surface. An even bigger problem comes from real-world observations of Zeta II Reticuli. The consensus so far is that the star has no gas giant planets in orbit, and in 2007, the Spitzer Infrared Space Telescope made the chances of the planet Calpamus and its moons existing even less likely, as it seemingly detected a debris disk around the star. This would imply that the system had not yet settled into a stable solar system, with planets still forming out of the disk of gas, dust, and rock. However, later observations from the ALMA radio telescope array found that the debris field Spitzer detected was found with high certainty to be a background signal. So there is yet hope for the discovery of a giant planet, with a ready-made name for it and its moons. Despite this inaccuracy, we can probably cut writers some slack. At the time of Alien's release, exoplanets were still the stuff of speculation, with the first confirmed detection in 1992. And, as we've discussed in other videos, the moons of gas giants, even in our own solar system, remain some of the most tantalizing prospects in the hunt for extraterrestrial life. So they were on the money there. Upon discovering these prehistoric signposts in the cave, Shaw's team quite quickly acquire funding from the Weyland-Yutani Corporation, a sort of Amazon of the future with extraordinary technological resources, and they make the 39 light-year journey to investigate Zeta II Reticuli in a ship called, drumroll, the Prometheus. The journey, according to the film, takes 2 years. 2 years. 39 light years in 2 years. 39 times the distance light travels in 1 year in just 2. From our current understanding of physics, it is simply not possible for anything with mass to travel faster than the speed of light. And from what we can see, the Prometheus doesn't seem to have any kind of wormhole-esque teleportation abilities. So we can assume that it moves under the power of some kind of propulsion system, like an ion engine we would recognize today. Even if we took 1,000 of the current best ion engines and made each of them 1,000 times more powerful, it would still take a 1,000 metric ton ship around 250 years to travel to Zeta II Reticuli. However, I believe we can work out what the writers were thinking when they came up with this traveling time. They would have been making use of a phenomenon known as length contraction, whereby distances shrink for fast-moving observers. Let's say the Prometheus was able to travel at 99% the speed of light. If we run the calculations and we ignore needing time to speed up and slow down, we find that, for the ship and its crew, the time needed to travel between the two stars would contract to around 2 years. So we found their magic number, but we still don't have an explanation for how they were able to reach these speeds. And even if they could travel this close to the speed of light, the calendar on the ship would only apply to the ship. Zeta II Reticuli would be 37 years further into the future, and so would the Earth. with the return journey bringing the same problems. In the case of the Prometheus, discoveries and events on Earth could render the journey completely pointless by the time they get back to Earth, if they ever do. This is a classic sci-fi obstacle, one that I explored in a video about Interstellar. So the franchise doesn't seem to have a good answer to the means of traveling great distances, but they have struck on an idea that space agencies considering long-duration missions have thought about: biological stasis, or as it's called in the Alien universe, hypersleep. Hypersleep could allow humans to endure lengthy space missions by drastically slowing their metabolism. This is not an alien concept to current science. NASA has considered the idea of stasis as part of its plan for human exploration of Mars, and Mother Nature has been playing out various phenomena of it for millennia. One study proposed the torpor-inducing transfer habitat, where astronauts would be put into a torpor state using therapeutic hypothermia. A torpor state is similar to hibernation, nature's answer to hypersleep. Hibernation in animals involves significant physiological changes, including reduced heart rate and breathing, with the brain remaining minimally active to control the state of other organs. This significantly reduces their metabolic rate, minimizing the need for food, water, and oxygen, and in the case of humans in space travel, would allow for a smaller and lighter spacecraft while ensuring that the astronauts arrive at the peak of their physical fitness, not withered and fed up. However, as of right now, hypersleep is not a viable solution for humans endeavoring to traverse the vast distances of space. NASA and other space agencies are for now focusing on developing living systems and preventative medicines that will aid the astronauts in maintaining good physical and mental health, which is no mean feat when in space, where you must contend with microgravity causing muscles to weaken, radiation damaging DNA and cells, and the punishing mental struggle of isolation and being so far from a human's natural home. So, although we are nowhere near able to travel the kinds of distances we see in alien films, especially not in the next 100 years, it's not infeasible that we might be able to suspend our space travelers in hypersleep such as Shaw, Ripley, and their crews did. But if theirs and other alien missions are anything to go by, we may not want to make those journeys for fear of what we could find. And that brings us on to the Xenomorph. The Xenomorph is one of science fiction's most terrifying extraterrestrials. Truly and unrelentingly alien in every sense of the word. But I'd wager that what makes the Xenomorph so terrifying is its similarities to some of the Earth's most gruesome inhabitants. By borrowing elements from parasitic organisms, rapid genetic adaptability, and extreme survival mechanisms found in nature, the Xenomorph's biology creates the perfect predator, survivor, adapter, and reproducer all rolled up into one. But how realistic are its infamous traits? Let's start with the life cycle. According to the films, a xenomorph starts out as an egg laid by the queen of its colony, the first of many insect comparisons. Dormant and inert at first glance, the egg is in fact a trap waiting to be sprung, for inside, a so-called facehugger is lying in wait. The facehugger is a crab-like creature with exceptional speed and strength, and it has one goal: find a host in which to implant the embryo it harbors, allowing the next stage of the life cycle to initiate. When the egg detects movement, or perhaps the increased presence of gases like CO2 from a nearby organism like an unsuspecting human host, the facehugger will leap out in pursuit. This is not unlike what certain Earth fungi will do, releasing spores to infect animals that pass by to continue their own life cycle. The creators of Alien were heavily inspired by wasps when designing the xenomorph. You can see the insect inspiration in its exoskeleton and general creepy crawly form. In particular, it is intended to mirror parasitic wasps like Cortesia glometara and the tarantula hawk wasp. These wasps lay their eggs inside the bodies of other insects or arachnids. The larvae that hatch feed on the host from the inside out, deliberately consuming non-vital organs first to prolong the host's life, ensuring that the larval wasps have a fresh food source until they are ready to emerge. Given that this already exists in the natural world on Earth, it's not ridiculous to believe that this could exist in more extreme forms in exoplanetary ecosystems. In the natural world, there are numerous examples of parasites that exhibit similarly disturbing behaviors. For instance, the parasitic fungus Opiocordyceps unilateralis infects ants, taking over their central nervous system. The fungus compels the ant to climb to a high point before it dies, allowing the fungus to sprout from the ant's body and release spores to infect more hosts. The ant, much like the human host of a xenomorph, is reduced to a mere tool for the parasite's reproduction. Another example is the parasitic barnacle Saculina, which infects crabs. Saculina, essentially a living needle, injects the cells into the crab's body, where they grow and eventually take over the crab's reproductive system. The infected crab is rendered sterile and begins caring for the parasite's offspring as if they were its own, all while its body is slowly consumed from within. This is the stuff of nightmares. Once the chest burster gets loose from its human host, it grows extremely rapidly into its final, lethal predatory form. But perhaps too rapidly. In many of the Alien films, we see chest bursters emerge quite small, but within a matter of hours, they are multiple times the size. How? We don't see them feed on anything in the meantime? This is a source of controversy within the Alien fandom. In the extended universe beyond the films, it's implied that the chest burster goes on a feeding frenzy in the ship's stockpiles, becoming a huge caterpillar before transforming all that material into the classic xenomorph. But since we don't see that in the films, I'd like to explore some other options. One theory is that the xenomorph combines another trait from insects with an ability of plants. Insects breathe through a network of tiny tubes called trachea, which extend through their bodies and open to the outside world called spiracles. Oxygen enters these spiracles and diffuses directly into the tracheal system, delivering oxygen to cells and tissues, bypassing the need for a circulatory system to transport oxygen. This direct diffusion through their exoskeleton allows insects to efficiently manage respiration without lungs. Plants sequester carbon through the process of photosynthesis, where they absorb carbon dioxide from the atmosphere and use sunlight to convert it into glucose and oxygen. The carbon is then stored in the plant's biomass. Perhaps the xenomorph is able to absorb gases from the air to facilitate its rapid growth, using some kind of photosynthesis-like process to convert the gas to muscle and tissue. There are a couple of problems with this theory, however. One is that the tracheal respiration becomes less effective the bigger the animal becomes. The volume to surface area ratio gets bigger exponentially, so quickly there is not enough surface area to dissolve oxygen through to supply the entire biomass. This is the reason why insects aren't so big nowadays, but were much larger when Earth had 300% more oxygen around 290 million years ago. We also see a few instances where the xenomorph is able to withstand the vacuum of space. If it did breathe through open spiracles, these would be a weak point in the exoskeleton, where material inside could burst out from the pressure difference. And a final problem comes from theories about what the xenomorph is made from. Some people think the creature must be silicon-based, which is much less readily available in the atmosphere of a ship. So if that were the case, it wouldn't have enough building blocks to grow so quickly. So, by whatever means, you now have yourself a fully grown xenomorph on board. It's fast, it's smart, it's ruthless. The odds are stacked against you for mounting any kind of defense against this thing. But even if you do manage to land a strike and pierce its exoskeleton, what comes spurting out? Acid blood. And not just any acid, but clearly some of the strongest acid in existence that can corrode through metal, layers and layers of metal.
Next deck.
Acids are defined by their ability to break apart other molecules by donating atoms that form stronger bonds. Acids are measured by their pH. The lower the pH, the stronger the acid. Hydrofluoric acid, with a pH around 2.1, is a classic example of a powerful acid. it is one that chemists will handle commonly, but extremely carefully, as it is capable of dissolving glass, metals, and penetrating tissue and bones due to the highly reactive fluorine it contains. The xenomorph's blood, however, would need to be even more potent, possibly similar to fluoroantimonic acid, the strongest acid known to science, with a pH of -31.3. This super acid is so corrosive it can dissolve nearly any material. If xenomorph blood were made of a compound like this, it could explain the rapid corrosion seen in the films. But if a few drops of this stuff can sizzle its way through the bulk of a metal spaceship, how is it contained within the xenomorph? I mean, our blood is essentially neutral at pH 7.35, and even a slight deviation will see you quickly developing acidosis, putting you in real trouble. So how is the xenomorph doing it? Short answer? Teflon. Yes, the material on your non-stick pans, that stuff. If the xenomorph's blood cells were lined with a material like Teflon, known for its carbon-fluorine bonds, which are so strong that the fluorine atoms in fluoroantimonic acid can't break it apart. This would prevent the acid from damaging the xenomorph itself. Some fans speculate that the xenomorph is resistant to its own blood because it is silicon-based lifeform instead of carbon like all life on Earth. Silicon could work similarly to Teflon in containing the xenomorph's acid blood, as it also forms very strong bonds that acids struggle to break down. However, even silicon bonds probably couldn't resist the destructive power of fluoroantimonic acid. And to add to that, there is very little evidence in the films that xenomorphs are silicon-based, and the fact that they can feed and grow inside a carbon-based human seems to actively contradict it. It's not clear why the xenomorph has acidic blood. It seems likely for defense purposes, in the same way that many reptiles on Earth will secrete toxic or irritating substances when provoked. But it could also be for energy, harvesting the power locked up in the acid's molecular bonds to power its attacks, in a similar way that a car battery does. Or perhaps the Hollywood writers just thought it would be cool. Either way, the acidic blood of this alien is one of the harder to believe aspects of its physiology. It's a very big ask for an organism that has to grow with fairly scarce resources available to it to not only produce an acid of this strength, but also generate organs and tissues that can withstand its ferocious corrosiveness. However, although clearly powerful, xenomorph blood is not the scariest chemical in the franchise. In the prequel, Prometheus, the scientists who descend onto LV-223, who have a somewhat casual attitude to personal safety, encounter a strange black goo. This goo, elegantly named This, seems to have been made as a bioweapon by an ancient civilization called the Engineers, and is somehow what all the biology in the franchise boils down to. You can trace the origins of the xenomorph and, also surprisingly, humanity back to the goo.
DNA. Match.
It's us.
But it has far more immediate and sinister implications for anyone who comes into contact with it. The black goo functions as a genetic accelerant and mutator, a substance capable of radically altering or even completely destroying an organism's physiology. For example, when the goo infects native worms on LV-223, they transform into hammerpedes, creatures with heightened aggression and acidic properties, reminiscent of the xenomorph's traits. This suggests that the goo can weaponize any biology it encounters, morphing it into the xeno direction. The goo's mechanism of action appears to be a violent restructuring of DNA, effectively hacking the genetic code of any organism it touches. This process could be similar to CRISPR, a real-world genetic technique used by bacteria to defend against viruses, and now also by scientists in creating new medicines. CRISPR edits genes by inserting new DNA sequences. The black goo seems to be doing the same, forcing them to express new, weaponized traits. This is seen when one of the crew members of the Prometheus is exposed to the goo, which alters his sperm. When he later has intercourse with Dr. Elizabeth Shaw, she becomes impregnated with a creature that eventually develops into a facehugger-like organism, leading to the creation of a xenomorph-like entity called the Deacon, without any direct involvement from an actual xenomorph. In that case, rather than existing as a single, definable species, the final form of the xenomorph might simply be the result of either the embryo or the black goo mingling genetically with various organisms, creating different forms depending on the host. For example, in Alien 3, a dog is infected by a xenomorph embryo, resulting in the Runner, a creature with dog-like characteristics. It makes sense with the name too, with xeno meaning strange or alien, and morph meaning form or shape. It's not specific, it's almost conceptual. It suggests that the classic xenomorph is less a species and more a manifestation of genetic combination with humans, leading to the rather unsettling idea that the xenomorph, in a way, has been inside us all along, a kind of dark mirroring of us. The influence of this chemical on the franchise is far-reaching across time and space. In one scene, it's seen seeding life on planet Earth, as one of the engineer species drinks a vial of it and his body and genetic material disintegrates and redistributes. In another, the artificial human, David, a whole other scientific rabbit hole in this series that we might get to in another video, is seen destroying an entire city of engineers with the goo and performing experiments to create new kinds of xenomorphs. Thankfully, there is no analogous chemical on Earth today. But with CRISPR, we are beginning to develop tools that can change the genetic makeup of not just embryos, but living organisms. Something we must surely take steps to keep out of the hands of dangerous actors, lest we want to end up creating our own downfall. As we shed back the layers of the Alien franchise, we find a tapestry woven from the threads of our deepest fears. Our scientific curiosity and our fascination with the unknown. The xenomorphs, with their terrifying life cycle, parasitic nature, and unstoppable predatory instincts, are the perfect embodiment of what might lurk in the darkest corners of the universe. But more than just creatures of nightmare, they are a reflection of our own world, drawn from the real-life horrors of nature and amplified through the lens of speculative science. So, as we look to the stars and imagine what might be out there, let's not forget the lessons of these films. The xenomorphs may be fictional, but the questions they raise are valid. How far will we go in our quest for knowledge? And when we finally meet whatever is out there, will we be prepared for what we encounter? What will the consequences be of discovering alien life forms? The alien universe is a stark reminder that in the vast, uncaring expanse of space, we may not be alone, but we might wish we were. Thank you for joining me on this journey through the science and fiction of the Alien franchise. Although no one can hear you scream in space, we can hear you down in the comments, so let us know what aspects of Alien you find most frightening and what you think we might have missed. Black holes, wormholes, and time dilation. All concepts of general relativity that Christopher Nolan wove into his 2014 film Interstellar in a manner we had never seen before. While many loved its groundbreaking, scientific take on the dangers of intense time dilation, as his group of astronauts in search of a new home for humanity found themselves losing years in minutes, there were certainly elements of the film and its ending that seemed strange. Towering waves sweeping around planets, black holes that you can enter and use to reach across time and space using gravitational forces. Interstellar at times felt like it strayed from science into science fiction. But what is the science and what is the fiction? What did the film get right? Where did it take artistic license and diverge from our current scientific knowledge? Can you really use a black hole to communicate ideas across space and time? I'm Alex McColgan, and you're watching Astrum. Join me today as we learn the truth about Interstellar. We will explore the numerous scientific phenomena of this film that underpin wormholes and black holes, and discover the realities of what happens when you bend space-time to its extreme. For those of you who need a reminder, let's begin with a quick plot recap. In the film, a disease referred to as the Blight takes hold of crops on Earth and starts killing them, causing a population collapse and technological decay as humanity focuses on farming instead of spacefaring. Our protagonist, a former NASA pilot named Cooper, finds himself at a hidden NASA base where they are working on plans to save humanity. Hope has arrived in the form of a wormhole, a tunnel through space-time that they have detected near the orbit of Saturn half a century ago, which is thought to lead to potentially habitable planets. In the film, they show the wormhole not as a cliché portal, but through distortions of stars near Saturn. So here we have our first piece of science to evaluate. This portrayal of a wormhole makes sense. A wormhole is an extreme distortion of the fabric of the universe, similar to a black hole, and would only really be visible through the light near its edges becoming warped. Wormholes are interesting. We have the theory and mathematics behind them somewhat solved already thanks to Einstein and relativity. Wormholes connect space-time to itself, resulting in a shortcut that joins separate points in space and even time to one another. The film uses a classic analogy for this, showing a pencil piercing a shortcut through a piece of paper representing space-time. Sadly though, although we have the theory, we don't actually have the means to make them, even if they can be made at all. There are a couple of problems with wormholes. To begin with, their creation. The scientific advisor for the film, Kip Thorne, released a few physics papers after the film to discuss the scientific advancements they made in its production. In a paper titled Visualizing Interstellar's Wormhole, he notes that it is difficult to create a wormhole out of nothing, as it would require the existence of backwards time travel. You see, once the two ends of a wormhole were linked, they would stay linked. Then, if you could time dilate one end for another by moving it very quickly, causing it to move slower in time than the other end, you could enter the end further along in time and emerge at the point further back in time, thus entering your own past. You could then, for instance, grab yourself and stop yourself from entering the first portal in the first place, creating a paradox where you both enter and do not enter the portal, breaking reality and also my brain. There are lots of mathematical arguments that advocate against this sort of thing, such as Stephen Hawking's chronology protection conjecture. Simply put, it states that the laws of physics would prevent wormholes, these closed time-like curves, from appearing in the first place. Admittedly, this hasn't been proven and relies on a bit of an appeal to common sense. Loops can't exist because we would struggle to imagine how they can exist. This is a problem we return to later in the film. However, the time travel aspect isn't the only problem with wormholes. Traveling through them is theoretically tricky too. You see, if a wormhole were to be created, the throat of the wormhole would soon pinch off and the shortcut through space-time would be sealed due to gravity forcing it to close in on itself. So, the moment Cooper tried to enter the wormhole, it would instantly close, ending his mission before it started, which would make for a boring film. To make a wormhole persist long enough that people can travel through it, we would have to use a mathematical hack. We pretend as if some exotic matter exists, which has negative mass. This negative mass would then have to be placed at the throat so that it can create opposing curvature, which would counteract the tendency of the wormhole to close, keeping it open in perpetuity. You might be thinking that this sounds made up, and you'd be right. We have never found negative mass, and have no idea how to make it, so this seems like a mere mathematical curiosity. So, while wormholes are allowed for in scientific fact, actually traveling through one is so far just science fiction. Still, without it, the rest of the film couldn't really happen, so you can understand why Nolan decided to keep it in. Whether or not this conjecture is true, this backwards causal relationship is baked into the movie. Not just because of the existence of the wormhole which implies it, but also with a reveal at the climax of the film, which we will return to later. While the existence of the wormhole requires some suspension of disbelief, the stunning visuals of the wormhole do not. In fact, the team behind the film used the theory of general relativity to mathematically model what a real wormhole would look like, which was, in fact, an impressive breakthrough of mathematical modeling. In a bonus scene for patrons and members, we explain how they were able to bring the wormhole and black hole from maths equations to the IMAX screen. Make sure to check it out. Now, let's move on to the next piece of science to evaluate. After the crew makes their way through the wormhole, they arrive near a supermassive black hole called Gargantua. Orbiting Gargantua are two promising planets that may be able to harbour life. The first one, Miller's planet, is deep in the gravitational well caused by the black hole. Some of the crew go down onto the planet, but within just a short couple of hours have skipped forward decades into the future, much to the misfortune of the crewmate they left behind, who had to live out those years at normal speed. This part of the film is absolutely plausible. This is gravitational time dilation in action, and is thoroughly proven experimentally. Gravitational time dilation is a result of the bending of space-time caused by massive objects. Time itself runs slower when you are gripped by stronger gravity. It even takes place here on Earth, between us and our orbiting satellites. Much like the crewmate left outside the gravity well experiencing faster time, a clock placed at the orbit of GPS satellites records 45 extra microseconds per day compared to a clock on the Earth's surface. GPS must take this effect into account to get calculations of your position right. If they didn't, your Google Maps location would quickly diverge from your actual position. It's crazy to think that the same underlying theory that explains black holes and time travel also helps us find our way home when we are lost. That in itself is Nobel Prize worthy. Of course, in Interstellar, the time dilation effect is taken to the extreme. In the ultra-strong gravitational well of a supermassive black hole, an orbiting planet could be experiencing severe time dilation compared to an observer much further out, so really the only thing to nitpick here is the size of the black hole in the sky from the view of the planet. In The Science of Interstellar, Kip Thorne states that Gargantua is 100 million times the mass of our Sun, and that this would mean that the black hole would take up half of the entire sky of Miller's planet to make the calculations work out. However, Nolan decided to make it look smaller in the sky, so that it would appear more striking when it's the focus of the story later on. Here is an example of where aesthetics won out over true scientific exactitude. Now, much like the crew down on the water planet, let's jump further ahead in time. We have the strangest, most mind-bending scene of the whole film to explore, the part where Cooper enters the black hole. In a bid to save the mission and to get at least some of the crew to the final planet, Cooper has to sacrifice himself, catapulting himself into the heart of the black hole to give others enough momentum to escape its gravity. Ironically though, this isn't the certain doom it first appeared. At the heart of the black hole, Cooper finds a tesseract, a representation of 5-dimensional space, where time is a physical dimension that he can move around in. He's able to use gravitational forces here to reach out to his daughter back on Earth across space and time, and bizarrely is able to give her the knowledge she needs to start the mission to the other planets in the first place. So let's ask the big question here. Is any of this theoretically possible? Let's start with simply the concept of entering the black hole. In a previous video I've made about black holes, I spoke about how they're actually quite hard to get into. Angular momentum can become near relativistic the closer you are to the black hole, requiring you to shed momentum before you can fall any deeper. That accretion disk you see around Gargantua is matter that is doing exactly that, spinning so fast as it tries to shed momentum to fall deeper into the abyss that the friction involved has turned it into a bright plasma. Seeing as this plasma can reach temperatures of millions of degrees Celsius, this might prove fatal for poor Cooper. But let's say that Cooper manages to find a route that does not turn him into superheated plasma on the way in. What would happen? Firstly, as he crossed the event horizon, the boundary after which even light can't escape, the light bouncing off his body would make it appear as if he were moving slower. If you were viewing this from the outside, you'd see the image of his body freeze and persist on the event horizon before gradually turning invisible. Because the light is being stretched by the extreme distortion of space-time, its wavelength would increase, and the light you receive later on would be more and more redshifted, until Cooper vanished from your view entirely. Cooper, meanwhile, depending on his angle of entry, would start to experience an effect known as spaghettification. Essentially, as parts of his body started to experience the passage of time slightly differently due to the gradient of gravity he was falling into, he would find himself slowly becoming more and more stretched. This pull would eventually snap him in half as the force of it overcame the bonds between his molecules. This would happen again and again until he was just a stream of molecules falling into the black hole's heart. This would not necessarily happen exactly at the event horizon. The event horizon itself is not truly a physical object, but rather is simply the mathematical point between gravity that is escapable and gravity that is inescapable. Cooper might not notice he was crossing it if it weren't for an obstacle known as the photosphere. There is a point in space along the edge of the event horizon where gravity pulls just the right amount to not let any light escape the black hole, but also doesn't pull enough to drag it in deeper. In effect, at this precise distance from the singularity, any photons of light that arrive enter an orbit they never leave. Over time, the amount of light here would gradually increase and increase. Most likely, when Cooper entered this specific zone, he would suddenly encounter a previously invisible massive spike of radiation that could very easily kill him, assuming he wasn't already dead from the accretion disk's plasma, or the spaghettification. There are lots of ways you can die when falling into a black hole, but let's say that he manages to get past all of that. Could he then actually attempt that last point, to speak across time and space using gravity? Honestly, it's a little unclear. The physics beyond the event horizon is murky at best, so scientists don't really know for sure what happens down there. But strangely, it does bear some passing resemblance to our current mathematical solutions on the subject. Our maths, as it stands, says that space curves so much that all the paths you can travel just lead you down deeper into the black hole. But there are some weird scenarios where you can end up arriving at points in your own past, which could allow you to influence what you do there. Which brings us once again to the idea of paradoxes. Paradoxes are all through the film Interstellar. What if Cooper did something in the black hole that killed his past self? That's 4 kinds of dead now, for those keeping track, thus stopping himself from going back in time later. Then he would never have gone back to kill his past self, thus saving his past self's life. But that would mean he was able to go back, so could kill himself. And on it goes in a circle. The film attempts to get around this circle using something known as a bootstrap paradox, where everything in the film always happened the way it was once it was influenced through time travel. Cooper used the black hole to teach people back on Earth data that they needed for a gravity equation, which allowed them to launch Cooper's ship in the first place. But the film showed that Cooper's interdimensional fumblings were present at the start of the film too. Cooper did what he did, and he had always done it. In a way, this closes the loop. But this is a little unsatisfying, as it still opens the question of what would have happened if Cooper had decided not to share gravity equation data with the past. It removes free will. As soon as Cooper realized that he was in a bootstrap paradox, he had to do what he'd always done, or the whole thing would collapse. This happens even more broadly as we learn that future humans, now sufficiently advanced, were the ones who created the Tesseract that allowed humans to be saved in the first place. But what if they decided to not create it? Then we're back in paradox territory, where the universe has to solve a thing happening and not happening at the same time. We don't really have an answer in physics for what happens with that. So this is an area where Interstellar becomes less scientifically certain. However, it does make for a mind-bending story. In the end, despite some divergences from science taken for dramatic purposes, Interstellar helped showcase the fascinating concepts from modern physics to a mass audience. It was able to show how time isn't just a rigid arrow, but rather, as the Doctor said, a wibbly-wobbly, timey-wimey thing, going at different speeds depending on what gravity fields you were moving through. Imagine you're looking to buy a house, some place nice for you and your family. Except instead of a house, you're looking for a planet. And it's not just your future, but for all of humanity. This was the mission that faced 12 brave astronauts in Christopher Nolan's 2014 film Interstellar. With Earth on the brink of agricultural collapse, humanity's only hope seems to be abandoning the planet in search of a new one. The Lazarus mission sent 12 astronauts to 12 candidate planets to determine which was best suited for a human colony. 10 years later, the Endurance mission launched to explore the 3 planets that had sent back the most promising data. In my last video about Interstellar, we covered the famous wormhole, supermassive black hole Gargantua, and how the film portrays time dilation. Today, as promised, we're diving deeper into the exoplanets the Endurance crew visited. Oh, and if you haven't seen this film yet, pause this video and go and watch it before coming back, because there will be spoilers. I'm Alex McColgan, and you're watching Astrum. Join me today as we explore the real estate of the Gargantua Pantagruel system, with Miller's towering tidal waves, the icy and isolated Mans planet, and Edmund's rocky terrain. We'll dig into what the movie got right or wrong about these exoplanets, their similarities with known planetary bodies in our own universe, and how habitable they really could be for a permanent human colony. To get started, let's brush up on Gargantua. Gargantua is a supermassive black hole some 10 billion light years from Earth, and a whopping 100 million times the mass of our Sun. Gargantua, like most genuine black holes we've discovered to date, rotates. It has lots of angular momentum which causes it to spin. As black holes spin, they also boost the rotation of their accretion disk of gas and dust. In Interstellar, this is what provides light and warmth to Gargantua's orbiting planets, Miller and Man. Miller's planet is a water world with knee-deep oceans and 1,200 meter tidal waves. It orbits incredibly close to Gargantua, just on the cusp of the event horizon. But wouldn't this kind of proximity be too dangerous and volatile to be habitable? Is this kind of proximity to a black hole even realistic? Actually, some researchers say it is. They argue these so-called planets wouldn't be so different from planets orbiting stars. But rather than form in a star's protoplanetary disk, they are thought to form in the black hole's accretion disk when ice-covered dust particles collide and fuse. Eventually, they gain enough mass to have a gravitational pull of their own, drawing more and more matter in until a hard planet is formed. Okay, so if planets do exist, what is their space environment like? Well, for starters, black holes emit a lot of radiation, primarily through hot, accreting gas. This accretion power is immense, orders of magnitude more than anything we could get from nuclear fusion. One paper suggests a planet like Miller would be completely surrounded by a 6,000-degree blackbody radiation field. Dr. Thorne, the Nobel Prize-winning physicist who consulted on the film, disagrees. In his book, The Science of Interstellar, he argues instead that Gargantua's disk is comparable in temperature to our Sun's surface, so emits lots of light but little to no X-rays or gamma rays. He also says the accretion disk is super thin and confined to Gargantua's equatorial plane. Such disks are actually possible around black holes that haven't ripped up a star in the last million years or so I suppose the film doesn't actually veer off from reality there. Unlikely, but not impossible. Okay, but how can Miller maintain a stable orbit around a black hole as large as Gargantua? Like planets orbiting our own Sun, Miller's planet has its own motion. If it was going fast enough to escape the Sun's gravity, it would shoot right past. However, if it was going slowly, it would get pulled in entirely by the Sun's gravity. The same is true for Gargantua. A planet in a stable orbit would only be possible if Miller's planet was going fast enough, not to be pulled into Gargantua's immense gravitational pull, but not so fast that it shoots right past it. Though this seems virtually impossible, Dr. Thorne hypothesized a sweet spot that could exist where the centrifugal force of the planet balances out the gravitational force pulling it inwards. However, the real issue isn't the planet's orbit, it's the planet's formation. Is it even possible for smaller, slower objects to coagulate together to form a planetary body so close to a black hole? In 2019, a group of physicists showed it is possible, but only if the planet formed within the accretion disk. Dr. Thorne aligns with this in his book and takes it a step further, stating that it's actually not possible for Miller's planet to exist outside the accretion disk. This presents a problem, as in the film, we see the planet orbiting well beyond the accretion disk. It is in the wrong place as far as the physics is concerned. But sometimes you have to take creative license and decide on fiction over fact to get more visually impactful images like this one. Being so close to a black hole brings out another quirky feature: time dilation. In the film, time on Miller passes 60,000 times slower than on Earth. Given where the planet is located, would time dilation actually be this severe? While researching this video, I came across differing opinions. Some think yes, it is possible, while others deny it, saying time dilation is only felt once you're inside the accretion disk, much closer than Miller's location in the film. According to Dr. Kipp, for this kind of time dilation to be realistic, Gargantua would have to spin at 1 in 100 trillion parts slower than the maximum spin possible for a black hole of that size. Incredibly unlikely, but technically not impossible. We can't discuss Miller's planet without discussing its waves. Being so close to Gargantua, it is under enormous tidal gravity. Dr. Thorne wrote that this most likely would make Miller's planet football-shaped along its equator, bulging strongly toward and away from the black hole. He also postulates that being this close to the black hole, Miller's planet would have to be tidally locked. I'm not sure how a tidally locked planet would be able to remain a water world. Surely half the world would be ice and the other half super hot. But if we continue the thread from earlier and accept that Miller's planet was meant to be located in the middle of Gargantua's accretion disk, then the heat wouldn't be one-sided anyway. Speaking of water, let's talk about Miller's waves. The film would have you believe that being subjected to such intense tidal forces gives rise to the colossal tidal waves we see on screen. They can be compared to tides here on Earth, which are dictated by our sun's and moon's gravitational forces, but on a much larger scale. Dr. Thorne himself admits that the only way he can make the equations work is by making Miller's planet rock back and forth relative to Gargantua. But that would require a third body, very close by, like another large planet, to keep its orbit eccentric. A second theory he proposes is that the tidal forces deform the planet's crust, leading to enormous tsunamis, but that still depends on something rocking the planet. Perhaps the best Miller analog we know of is Jupiter's moon, Europa. Much like Miller's planet, Europa has an eccentric orbit, arising from the gravity of the other Galilean moons tugging on it. This orbit also cracks its crust a lot, and creates tides in its subsurface ocean that stretch and relax the moon's surface. Overall, Miller's planet doesn't seem to be very hospitable at all, as the crew of the Endurance mission would discover. The film got this right, so we follow our protagonist to the next destination. The second planet the Endurance crew visits is Man's planet. It's a harsh, icy world, also orbiting Gargantua, though not quite as closely as Miller's does. There's no mention of time dilation here, but there are other unique features that make this planet fascinating. As we discover through the course of the film, Dr. Mann falsified data to make his planet appear more habitable than it actually was, in order to be rescued by a future crew. He claimed there was a rocky surface below, with breathable air and organic material, though this was never actually found. Instead, the whole planet seems to be a frozen world, a large sponge-like network of ice mountains, caves, and crevices surrounding big voids, with frozen clouds in the upper atmosphere. In order for frozen clouds to remain suspended, they have to be less dense than the atmosphere. Call me a skeptic, but this seems highly unlikely. Dr. Thorne theorizes the clouds are most likely frozen CO2, which has a density of 1.55 grams per centimeter cubed, assuming Earth's atmospheric pressure. An ammonia-rich atmosphere would be closer to 0.00077 grams per centimeter cubed. No chance of floating dry ice in ammonia gas, unless the atmospheric pressure on man is wildly different to where these numbers would change drastically. In any case, the film doesn't go into any explanations about this, so we'll just assume creative liberty was taken here to emphasize the visual differences between Miller's and man's planets. It is thought these ice clouds sublimate, repeatedly freezing and evaporating, then freezing again. It's thought that this could be due to the eccentricity of man's orbit about Gargantua, which causes the planet to heat up and cool off, depending on its distance from the black hole. It seems Nolan took a lot of artistic license with man's planet. Because of this, it's hard to compare it to anything in our universe. So far, we haven't discovered any exoplanets with ammonia-rich atmospheres. We have found plenty of cold exoplanets though. This exoplanet, an icy super-Earth 21,500 light-years away, is one of the coldest known exoplanets we know of, reaching temperatures as low as -220 degrees Celsius. Like man's planet, it is not a good candidate for a human colony. Let's turn our attention to Edmund's planet. After leaving man's planet, Cooper and Brand don't have enough fuel to make it to Edmund's planet, orbiting the star Pantagruel 1 light-year away. After slingshotting around Gargantua at a cost of 51 years due to time dilation, Cooper jettisons himself to shed weight from the Endurance and get Dr. Brand to Edmund's planet. However, it's unclear how Brand would have decelerated into orbit around Edmund's. One option is by slingshotting around another black hole, but this isn't shown in the film. Edmund's is a rocky planet with clouds and a breathable atmosphere. From this, we assume it to also have a surface water source and a biological source of oxygen gas. This could be from soil bacteria, which is assumed to be compatible with Earth-based life, since the film closes with a human colony populating Edmund's planet. Edmund shares many similarities with Earth: similar gravity, breathable air, arable soil, and potentially liquid water. It doesn't appear to be tidally locked either. Some interstellar fans compare Edmund's to an ancient Mars, back when it had oceans. By the end of the film, Edmund's planet is shown as a viable option for human colonization. We just need to develop hypersleep pods and find a nearby wormhole first. And with that, our grand tour comes to a close. So, which planet is most likely to be able to support a human colony? As we explored, Edmund seems the only viable option, even though we didn't see much of it. But I suppose that would have made for a much less exciting movie. Overall, the film did a pretty good job of trying to remain scientifically accurate. A few creative liberties were taken to enhance the storytelling, but that's why we go to see a sci-fi movie instead of a lecture. The power of science fiction is its ability to make us dream. And even though we are very far from colonizing other Earth-like planets, Interstellar does just that. It encourages us to keep that spark of wonder alive. Maybe there's someone out there looking longingly out at us too. Which planet would you most like to visit? Let me know in the comments. Thanks for watching, and see you next time. Thanks for watching, and thanks to our crew of Astromnauts over at Patreon who help us make science knowledge freely available to everyone. Chasing the algorithm can be hit and miss sometimes, so your contributions help us keep making the content we love. And if you haven't already, but you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.